Welcome. This talk is called Reactive Options for Groovy. My name is Steve. I work for a company called Third Channel in Boston, Massachusetts, in the USA. Let's talk about asynchronous data and reactive programming. So, when we say reactive, it's kind of a buzzword lately, I'm sure you've all heard of it. But what exactly do we mean? So I think there's several definitions that are floating around in the internet. The term to me, I think, means three things. First, reactive programming, the actual concept. It basically differentiates itself from standard imperative programming, where that imperative, if I assign the variable a to equal the values of variables b and c, A will equal those values at that moment in time, or A will equal what B and C were at that moment in time. But in the reactive sense, A equals B and C whenever B or C changes value. So, as an example, we've all been sort of doing this. Yes, thank you. We've all been doing this for years without maybe even realizing it. UI programming is inherently reactive. When a user pushes a button, that updates some sort of internal value about what's happening, and then the interface generally reacts to the user's Okay. It's going to be tough to read without that's done. Okay. So UIs are inherently reactive because they respond to user. A reactive system is the second definition, I think. And then there's the third definition. I think of reactive extensions and reactive streams. Yeah, it's really bad, isn't it? Yeah. That's really all right. Anyways. Well, let's try and muscle through this again. What if I can invert it and make it black with white bits? So I mentioned the two briefly because I think all three are related, even though they're all slightly different. But today is mostly going to be about reactive systems and RX. And I think these concepts are the most exciting, and they've been gathering a lot of traction or attention lately. So for today, I'm going to briefly talk about what reactive systems are, what reactive streams or reactive extensions, since they have the same name. Go over some some options that we have as Groovy developers, and then show two quick demos. So first, reactive systems. So let's talk about why we need to use reactive systems, or why they're so interesting. Can you hear this sort of a document called the Reactive Manifesto? So this is going to be a quick summary of this manifesto, and I'll get more into what this is later. But basically, the internet is growing, obviously. The number of users actually use the internet on a daily basis is estimated to have grown from 750 million to nearly 3 billion in just 11 years. 750 million to 3 billion, half the world. And even with this increased demand, users are expecting their browsing experience to respond as fast as possible. Almost unrealistic demands on the performance of web applications. And users tend to get angry and impatient whenever your site is slow or unresponsive. I borrowed this slide from a guy from Google named Ilya Grigor, who introduced, I think, this idea that it's called the 1,000 millisecond time to glass challenge, which basically states that your site should render to screen or to glass within 1 second of user interaction. Google did a study, or I think it was Google, did some sort of, there's a link there at the bottom, to this psychological study where they found that humans have their focus tends to go away after about 1 second. So if the user comes to your site and nothing responds and nothing happens within that 1 second, then the user's focus will switch, and they'll start to think about something else that they want to do. Yeah, I don't know if you've ever tried to start up like a Grails app or something. It takes long to build, and so then you switch over to do something else, and you're distracted and you forget. It's a similar sort of concept. I mentioned this in my talk yesterday, but there was Amazon also did a similar study where they found that if they intentionally slowed down the traffic of their website by 1,000 milliseconds, or excuse me, 100 milliseconds, a tenth of a second, then that resulted in a loss of sales of 1%, which for a company like Amazon is millions of dollars. Because users get distracted and they need to do something else, and of course, you're slowing down the site, you end up taking less money for it. Furthermore, the scale of the internet is growing tremendously. The number of users in 2012 of just one site is equal to the entire internet user base of just 6 years before that, in 2006. Now, granted, that site is Facebook, but it just shows you that websites are facing increasing scaling problems. Applications need to handle as many users as possible and as efficiently as possible. Many frameworks and server technologies that are still in use today rely on one request per thread approach, which can be a little bit inefficient in how you use the resources available to you on your system. So the Reactive manifesto calls for 4 principles to try and achieve what they call a reactive system. The source of these reactive systems can be traced to this document, which is called the Reactive manifesto. This has gone through several revisions over the past several years. Yeah, it's good try. The most recent edition was made this past Pember, where they shortened it because it was actually like dozens and dozens of pages long. And they realized that no one was going to read the whole thing, so they shrunk it down to a page or two. And they simplified it to basically point out 4 principles that a system should have, or 4 features that a system should have to be reactive. The first, the application must be responsive. This is essentially the ultimate goal of an application, is to respond to the user as quickly as you possibly can. So it's going back to speed. It seems like it's speed is very important. A more responsive application is a more pleasing experience for your users. The faster your application responds to their input, the less time they'll just sit staring at it, and the happier they'll be. Next up, your application must be resilient. The resilient principle says that we, as software developers, should have the mindset that at any given moment, your code is going to break, something is going to malfunction. So, I mean, think to yourself, how coupled is the code in your current project? How many of you have systems that are held together by quick hacks, or some large amount of technical debt? And how dependent are your systems on other services, third-party systems, and things like that? What happens if any one of them goes down? So the resilient principle says that we shouldn't be scared of our application, but we should embrace it. So a reactive application is resilient today. If one component goes down, the others should be able to pick up the slack. Third-party service is unavailable, your app should be able to handle it. For example, if you were making I used this example in my talk yesterday, but in an e-commerce application, and you had, you have the product browsing section, and you have the service or a component that allows users to place orders, and you have a component that charges users credit card. If the call to American Express to check to see if the credit card is valid goes down, your website should crash. You should basically say something like, "Oh, I'm sorry, we can't place orders right now, but feel free to keep browsing, add things to your cart, and we'll come back to some things." And so I use this. I also must not yesterday, but independent components should fail independently. Next, a system should be elastic or scalable. Your application should stay responsive under load, and it should react to changes in its workload by increasing or decreasing resources based on the current demand of the system. And lastly, third, no, this is last. Reactive applications are message-driven asynchronously. And I think this is the most interesting part, at least for this whole reactive topic. This calls for building highly concurrent systems that talk to each other by passing messages. However, the reason why this is fascinating, I think, is that we humans are not good at dealing with concurrency. Things like thread safety is a hard problem. So reactive systems call for using techniques and libraries to abstract away some of these concurrent procedures so that we don't have to think about it too much, because again, it's really hard. And the Reactive Manifesto recommends two different approaches to this message-oriented, asynchronous driven applications. The first is an event-based approach. In an event-based approach, communication with the system should be done via asynchronous, immutable events, rather than long procedural code. So if something happens within your system, that component emits an event, it tells the world that this particular thing happened, and then it's done. And other components can react to that event if they want to. This naturally, by the way, promotes highly decoupled code. The sender and the recipient of the messages can be constructed without having to know or care about implementation details of the other. And this is a very important point. I think it's the most important facet of reactive programming, as the others can naturally be sort of adopted. By generating event or message-based approaches, you separate this highly coupled code, smaller components, easier to understand. Let's see. The one that they really recommend, probably because they also develop a program which uses this approach, is an actor pattern. And this is a little bit confusing. I'm not sure I fully understand it, so I'm going to do my best here to try and describe it. An actor system is very complicated. An actor is a small code block. It's essentially a function that knows how to do one specific thing. Actors are not accessed directly, but instead you generate actors within something called an actor system, and then you pass messages into it. And you interact with the system and not the actors directly. The system then abstracts the concurrency for how these actors are running. So underneath the system, the actors may be running in a thread pool, for example. And actor systems are highly scalable because the concurrency is abstracted and away from you. You're just dealing with this sort of black box system. You can under the hood replicate the system or distribute it across multiple actual independent machines, and then the code will note how to send the messages back and forth on the distributed system. What's interesting though is that with an actor model, like I said, you don't talk to the actors directly. Instead, you send messages into the system. And the actors themselves, and this is where it differs, I think, from the event-based approach, the actors have to then know which other actors to fan out messages to. And each actor has essentially a mailbox that these messages get passed to. It's very confusing, but it's interesting. But I think the key point just to take away is that it differs from the event-based approach in that you have to know which actors are to get the next message. With events, you just emit the data. But the most important point is that both of these systems, what these systems have in common is that they're entirely asynchronous. They abstract away concurrency problems, but they're also not blocking any resource, or they're using as few resources as possible, and not blocking a thread while they're doing some calculation. Okay, next up, reactive systems or reactive extensions. I like to call them streams. or reactive streams, but I think the official title is extensions. That's why you see RX. Reactive streams, the idea for these reactive extensions came out of Microsoft's cloud programmability team. It's a long tweet. I don't know. Sometime before 2010. It was designed as an interface for integrating multiple asynchronous data sources in the cloud. They were using it, the idea was to try and have one interface that you could use when pulling data from a bunch of different services in their cloud system. And then around 2010, they open sourced this particular feature. And it gained popularity in around 2011, because GitHub decided to use this library for their Windows client. And then they loved it so much they used it in literally every component of this application. And then they started trying to write their own separate version for other languages so that they could use it throughout their entire company. And then the collaboration with Microsoft and GitHub then put together essentially a spec about what these reactive extensions should be. I think perhaps to thwart them for GitHub sort of owning and bringing the reactive systems to the wider world. So then a couple years after that, many heavy hitters from the JVM community wanted to port this over and make this available in the JVM. So Twitter, a company called TypeSafe, which actually wrote the Reactive Manifesto. Netflix is another big one. They all came together and put another spec for specifically for the JVM called reactivestreams.org. And they decided to flesh out exactly how these reactive extensions would work in our world using the JVM. And as of a few days ago, we have several libraries available to us which fully adhere to the spec. They even wrote their own little program for the TCK, which actually will test various libraries and make sure they fully adhere to what's going on. The reactive streams were designed to handle messages that were passed asynchronously from different sources. The term they use is across boundaries. And so this boundary, this line, this division, could be another service. So, a microservice time, basically. This is a very interesting approach for handling data coming from a different service. It can also be just internal components within inside your application. Reactive streams are composable. Just step back 1 minute to describe that. The idea is that you're dealing with data coming in as a stream, which may initially resemble your common iterable, but they're designed to deal with potentially infinite data. Whereas your normal list or iterable component within, let's say, Groovy or Java, generally uses a finite or limited set of data. Streams are composable. Let's see if I can. For those of you in the back, this may be hard to see. So this is an example of a composable stream. So at the very top there, I have this particular service that's the sales stream value. I'm assigning it to a variable called an observable. Streams are based around some slightly confusing terminology. The base term is that a stream of potentially infinite data is known as an observable. And if you are using a stream, you are essentially observing the data as it comes down from whatever source. So the key term is an observable, which is a little bit strange. But you use it essentially like a normal list or iterable. So here I'm basically saying take this sales stream observable, save it into a variable called branch, and then that next value subscribe on is how I basically making this stream concurrent. So with one line, I basically described how I want my stream to operate asynchronously. If I were to remove that line, then the observable would act in a blocking approach and just operate in the current thread. But by adding that one line, it then gets fanned out to different concurrency models, which I'll get into later. I then take the variable, and then in two different places, I can have two different listeners on it, and I can build these things up in two different approaches and still listen to the same data as it's coming out in two different ways asynchronously. The other key observation I think here, which we'll get a little bit more later, is that these streams are highly functional. So in this particular case, I have this branch variable, and then I added a filter function, which basically means, okay, now I'm filtering out any data from this particular stream based on some functions. I'm then buffering it, which is essentially grouping it into chunks of 10. And then this subscribe function is basically saying, okay, I want you to start pulling this data in, and for every object you get, I want to take this, now it'll be a list of 10, and then do some operation on it. And then down here, with that same data that's coming through, I'm also filtering it, but in a different manner. And then in this particular case, I'm just logging an error if I see a particular type of event. Streams can be what are called hot or cold. A cold stream is similar to your normal iterables. The cold stream assumes that there's no listeners, and it's holding onto its data until the first subscriber comes along. And then so basically the first time someone writes .subscribe onto that stream, then it starts pumping data at that particular subscriber. Hot stream is emitting data even if there's no one listening, and it can potentially run forever. It's potentially infinite, and you have to actively subscribe to it, and then you can start receiving events. So if you're working with a particular hot stream, you might miss events. An example of a cold stream would be data I pulled out of the database, and then I'm just doing some operations on it. A hot stream could be, let's say I'm listening for all user events within my application. So I could track user mouse movements as an active hot stream. I may miss some if I'm not going to subscribe to it. Does that make sense? It's very confusing. I don't know if I fully understand it either. Reactive streams, and this is another key component, asynchronous common interface. But they also allow the subscribers to tell the observable, the observable source, that they're sending too much data. This concept is called back pressure. And basically what it is it allows the consumers to tell the source of the data, you're going too fast, slow down. This is a very hard concept because when you're looking at the documentation, you get a slide like this, or an image like this, and it's hard to make sense of what it's actually doing. By default, some of these libraries will give you two different ways to deal with too much data. I guess a good example will be, let's say I'm tracking mouse movements. Again, if I'm using UI, I'm tracking the user's interaction with my site. And every time I receive a data point, I write it to the database. Now, that is the writing to the database is a much longer operation than it is to send these mouse movements. If anyone's tried to apply a mouse listener in a client, but it generates a huge amount of data. I get more data than I could possibly write to the disk. So you have several options available to you. I could tell the application to what's called a buffer. So if you're coming too fast, buffer these events, and then I'll receive them when I'm ready. That's just generally fine, but I may fill up the application's memory, which will crash. So you can also just ignore events, sort of like UDP. If I'm getting data, it's okay if I miss some. You can also write your own custom back pressure approaches or functions, where you can basically say, maybe sort of like how Ethernet works, where you can say, okay, give me 5, okay, great, I handled that. I'll give you 10, okay, great, I handled that. Give me 20, oh no, that's too much, slow it down. It's also a little bit confusing, but you have to talk more about it later. Okay, let's go for a couple libraries that are available to us as Groovy developers. So we want to get to this demo. ACA is a fairly famous library that comes out of a company called TypeSafe that also writes the Reactive Manifesto. ACA is based on the actor model, which is probably why they push for it so hard. They also developed a library called ACA Streams, which uses which adheres to the RX spec, but it uses the concurrency model under the hood is the actor model. It's very interesting. So yeah, I should describe that. RX and RX3 are particularly, I think, famous right now, and they're a good, I think, baseline for if you're interested in this approach to start working with them. They come out of Netflix. A guy named Ben Christensen is the primary author on this. It's bringing these reactive streams to JVM and making them pretty accessible. They're somewhat infamous for having these colorful, but often confusing diagrams that describe how the functions work. And so this is fairly simple. A scan function. But look at this one. So you get these crazy diagrams, which are very bright. I don't understand what that means. The definition, that's English. I don't know what that means. It doesn't help to figure out what it is. You just have to sort of play around with it. But basically, the join function does exactly what you might think it does and helps you join items together. But that's super confusing. So part of the difficulty in working with these reactive streams is sort of deciphering what the function would do. Next, we have the Rack Pack. And if I wasn't doing my talk right now, I would be at the Rack Pack workshop doing this again. So Rack Pack is very interesting, and then it's a HTTP application server, very non-opinionated, but it's built on reactive streams, netting, and uses Java and Glovo. But if you think about it, this is probably one of the best examples of a native reactive system. It's using non-blocking I/O as the base of it, and then using reactive streams on top of that. I would learn streams first before you try this, because it also does not use your standard servlet model too. But I'm very excited to try working with this application. Next, we have a library called Reactive, which I like, because it fully implements the reactive stream spec, but it also gives you the reactor pattern within your Java application. So the reactor pattern can be used by things like Vertex, and I'm pretty sure it's what Node.js uses, on top of Node is. And it's built on top of this thing called the LMAX disruptor, which uses the ring buffer pattern. So the disruptor, so LMAX is a financial trading company. They're trying to build the fastest trading platform in the world. And they also kindly open sourced their key piece of technology, which they call the disruptor. And so the Reactor library uses that to achieve this high-performant reactor. So a reactive model is kind of an event-based loop. So you put functions on this, essentially a ring, and so it'll go through. If a function needs to be executed, I don't know. I'm not fully describing it. I don't understand it. But I really like it because what it allows us to do. And here's a quick example of using Reactive. Let's say our e-commerce app. Let's say we had a function that placed an order and we weren't using Reactive. I might have to, let's say I'm placing an order, I might have to check that, make sure the order doesn't have any errors. And let's say that I have to execute some sort of long-running job, some sort of abstract long-running job. Let's say I have an inventory service, or I need to see if I have inventory available. I need to bill the user. I need to send them a confirmation error, or if there's no inventory, I send them a sorry, we didn't have enough product. Please try again later email. It's a very naive way to do that sort of thing. But let's say if each of these service calls take a long time, this is a horrible example that blocks the thread at every single one of these steps. This is calling this sort of third-party check. this slows down the request not only for the end user, but for any of your other users who are trying to get in and place orders too. So don't do this, but instead, we can do something like this, where I have an order that's created asynchronously, where I basically say, okay, save the order. If there's no errors, emit an event on the reactor that this order was created. And then I'd have other listeners on the reactor. So I should probably step back and say reactor's a message passing event-oriented approach. So I emit an event that the order was created. I have a particular service that's listening for it that then executes my long-running job. I have the inventory service that's also listening for an order created, that then checks to make sure that there's inventory available, and then asynchronously, based on that result, emits another event that's either order inventory true or order inventory false. So that's sort of a dynamic event that I generate on the fly. And then I have two other services, some other services, the money service, which is listening for a successful check on the inventory, which then will bill the user, and then the email service, which is listening for successful or failure order inventory checks, which will then send a confirmation email for the failure email, depending on the result of the transaction. And this is all happening asynchronously. So I take the order, commit the event, and then I go back and read taking the form. This is all yeah, absolutely. I mean, this doesn't necessarily have to be on the same system. I could turn this into a that event doesn't necessarily have to be on the same system. It could be distributed on another one. I don't know exactly how to do that because I've never tried it, but it's an option available to you. It works really well. We have a couple of services using this in production. One of them it doesn't work so well because I'm running into it's mostly good, except it's just there's one service that I have my own fault where I'm getting a hibernate exception. This multi-threading stuff. That's a whole other conversation. Anyway, so I also think this approach is easier to test too. So if I'm trying to unit test or integration test, I can simply test this by simply emitting events rather than having this big long code block to try to bug. It's much easier to test, I think, collaborators and things like that. What about Java 8 streams? I don't know if anyone's thought about that. Why didn't you mention that earlier? It's very interesting. Java 8 streams they're built into the language, right? But they're meant for finite variables. And so again, the observable is sort of inverted, where it's a little bit hard to describe the difference, but so the observable again deals with potentially infinite data. Java 8 streams is designed to sort of help you deal with your normal finite iterables. So I think the key differentiator is the Java 8 streams and the streams API is more about pushing data, pulling data from a particular array, let's say, or a list. But the observable is about a data source pushing data at your listener. It's a subtle difference, which again, I don't fully understand it in English. And the Java 8 stream doesn't have a concept of back pressure either, which is an important component of the reactive stream to be able to tell the source to slow it down. Okay, 9 minutes left. Let's see if I can do a quick demo. So, turn off. Okay, I'm going to try to zoom in. So I have two examples, one using Akka and one using RX Java. I'll do my best to zoom this in. Has anyone here seen the TV show It's Always Sunny in Philadelphia? No? Yes, okay. So it's basically it's a show about a bar and a bunch of horrible people. So I made an example using the actor pattern, inspired by the concept of actor, to try and create an example of how this might work. So I made a Spring Boot application which uses Akka and Groovy. I'm not sure the best way to show this. So with an actor system, when I'm using an actor system, I generally do start up your system by doing an actor system.create, and that generates this, again, this black box within your application. And then you have to tell it about your various actors. In this case, I have a bartender actor, and then four instances of a drinker actor. They're all named, and then I tell one of them, and then I basically I start delivering messages by telling the actors about particular data. So basically what I'm doing is I'm telling the actor called D that there's a new order with a value of 5, and it's for another actor called Charlie. Same thing for an actor called Mac. Same thing for an actor called Dennis. Same thing for an actor called the bartender actor. So basically, the scenario is the drinkers are ordering pints, and then the bartender is pouring the pints and sending messages, and this is all being done in an asynchronous, distributed way. So the bartender receives either orders or empty pints. So in this case, receiving an order, she increments, or the bartender increments the number of pints that are out in the world, pours one, and then passes it back to the person who ordered it. And this is done by accessing this variable that's automatically injected into every actor called the sender. So an actor knows about the message it received and who sent it to them. So the bartender knows that they received an order, and they know who sent the order to them. They also know, in this case of an empty pint glass sent back to them, they know who the sender was, and so they thank the sender for returning the clean glass, or the drunken glass. The drinker and receives full pints, drinks it down, and then sends empty pints back to the sender, which in this case is the bartender. Actually, systems are very confusing. Then I have two types of messages in order, which just has a quantity. Remember earlier I talked about how events should be commutable. Groovy has a great AST transformation called commutable, which helps write these messages. Because otherwise, without that, you have to write final int quantity, and then add exceptions if somebody tried to manipulate that value. Anyway, so if I run this, what should happen is get a bunch of log messages which are horrible to visualize. This is going to look gross, like this up on the screen here. Basically, what's happening is you can see each of the actors on the different threads receive the bigger pints. They drink it, and the bartender saying, "The pint is ready. Let's hand it off to Frank." This is pretty hard to read. I'm sorry about that. Okay, so what's happening is that the pints are being sent out, and then at the end, they're all being collected back up at once. That makes sense. So the bartender passes out all of the pints, and then at the end, they're queued back in her mailboxes, so that once she's done pouring all the pints, then they decide that the effect is that she ends up receiving the data all back at once, which is why you see these, thanks for the pint, there's still 17 left, 16, 15, 14, 12. And she accumulates all the messages back at the end. But so that's not quite as interesting, I think, as this other example, which is using RX Groovy. Over here. Created a little library that uses RX Groovy, which tries to simulate what I call a widget factory. And so this widget factory generates several different types of products, and then there's a stream here, a hot stream that is generating events to try and simulate sales. So we have some products, and then we have this this observable stream, which is every 2.5 seconds, basically sending a sales event throughout my observables, stream. So listeners can access the sales stream and receive these sales events and then respond to them accordingly. So I have an inventory service, which is the slide I showed you earlier, which is receiving these particular sales events and then filtering then deducting inventory, and then incrementing the amount of money that we're making by all these sales occurring. I have a report service, which is also listening on the same stream, and then for every sale that goes through, it lets me know about it. And then if I sell a particular widget type of a sprocket, it's very excited that we sold that particular type, and so it also lets me know that in addition that particular event was a sprocket. So essentially what's happening here is that I emit a single event, and then multiple services can observe that particular event asynchronously. And I don't have to worry about the concurrency model and this is done by simply adding this subscribe on function to my particular chain. So in effect, what happens if I run this? Yeah, sorry, I should have realized that looking at the console is not super fun. But I don't know if you can see, it's hard to read here, but I encourage you this code will be available, and I encourage you to take a look at it a bit later. But essentially what's happening is that you can see instances of my individual services, each responding to the particular event at once. So like I have, so like I can see that this particular widget of type foo just sold 5 units, and we made 71,000 cents. And then down here I know that it was a particular sprocket got sold, and so it lets me know about that. There's a little interface where I can look at the particular sales that are being reported. So I can see that there's a little breakdown by the different types of widgets. I can see how many units were sold and how much money we made, and then I'm converting it into US dollars as well. The code for that is kind of interesting too. So I have the sales controller that's listening on a different stream, which is essentially just looking at the current widget side. This is a finite stream, basically looking at the data coming out of my database. And then it's using this group by function to split them out into their different types, and then individually doing essentially map reduce on the distributed values, aggregating them, doing some mapping operations, and then reducing each of those back into one JSON object, and then sending that to the screen. Also asynchronous. Yeah. Okay. Any questions? I think that's all I have for a demo. Yeah. And I'm running a little bit late too, so I should probably slow down. Okay. There was a lot. There's a lot of information here, and there's a lot of information here. I really like this approach of thinking about things in terms of the stream-oriented way. If I had more time, I would go over some examples of your common for loop and show you how just about every for loop that you can think of can be easily broken down and rethought of as a stream. Once you do that, once you start thinking it that way, then you can start applying. You can move to what I think is the next step, where you start thinking about how this can be done asynchronously. And the trick with that is that you just add that function, and now your particular for loop is now operating in an asynchronous manner without much effort. I think it's very, very powerful, and it's it's very important as we go forward and start making these large-scale applications. And I think this is the key component to how you get it done. Okay, with that, I think I'm done. If anybody has any questions? Yes?
Two parts that are slow are not is not reactive stream. Two parts that are slow cube.
Two parts.
It's not a kind of reactive stream.
So, I don't think it's a reactive stream. G-parse is great for parallelization, and I haven't really been following it lately, but in order to actually be a reactive stream, it has to follow the concept of the back pressure to be able to basically tell the source to slow down, which is not something you're going to use immediately if you start using this. Like, I'm only just getting into dealing with that concept right now. And that's why it's a very subtle difference, but it's a very powerful one. I've heard, I haven't used it yet. Yeah. Any other questions? Yes.
How do you think this model fits with this microservices architecture we were talking about?
I'm glad you asked that, because I don't know if anyone noticed it, but maybe use some of the exact same words as in the presentation I gave yesterday. I think these two go hand in hand, and I think they're fundamental towards building large, scalable applications. And I think one of the key giveaways is that this was originally built for cloud environments, where you might actually where microservices fit in very well. And at least the reactive systems principles are directly applicable to microservices as well. The idea of being resilient, the idea of being scalable and elastic, the idea of being responsive. I mean, it's all intertwined, I think. Yeah. Good question. That's two parts of both very good question. Anyone else? All right. So with that, I think I'm done. Thank you. Thank you all.